Hello and welcome to the section 2.5 lecture today for our Bridges Math probability class. Today we're going to be looking at determining what it means more mathematically when we have combined events, and just kind of looking at some of the cases where it happens. What does that mean the probability is equal to kind of give us a better look. We've spent a lot of time on, is it independent or dependent? Is it exclusive or inclusive? Now we're going to kind of use those ideas to come up with some probability calculations. The first thing I want to look at are the problems from the day before, the last four problems. What these really come down to is, what does it mean to be exclusive and independent? Because those are the main questions here. Exclusive means that the probability of a couple different things. A or B is equal to the probability of A plus the probability of B. And again, this is exclusive. It also means that the probability of A and B is equal to 0. We're actually going to use that one a little bit more. The reason we're going to use that is that the idea of independent, so that's exclusive, independent means that the probability of A and B is equal to the probability of A times the probability of B. So what does that mean? Well, why would we need those ideas, and how are they going to help us to figure out these kind of all or nothing responses here? The first one says all exclusive events are independent. The problem with that is if two events are exclusive, then the probability of A and B is equal to 0. So unless the probability of A or B is equal to 0 themselves, that can't really be the case. Okay? Because the only way to multiply two numbers together and get 0 is if one of them is 0. And what this one's saying is, if an event is exclusive, or if this happens, then it's guaranteed to be independent. Oops. Which would mean that 0 would equal the probability of A times the probability of B. Now, again, the only way for that to happen is if either this is equal to 0 or this is equal to 0. And I feel like that's something that we can kind of assume isn't going to be the case. Because when we're talking about this, we're talking about that all or nothing situation. And probability of A or B being 0 isn't an always kind of a thing. All right, so this one's false. The second one says, well, if they're exclusive, then they're dependent. Well, and what dependent really meant was that this, basically, that this equation doesn't work out. But just because that equation doesn't work out also doesn't mean that that all this happens, right? It doesn't mean that A and B is equal to 0. I mean, that I can find times that does work. Flip a coin. Event A is it lands on heads. Event B is it lands on tails. Those are definitely exclusive. They're also dependent, but that's not always going to be the case. Okay, and especially with exclusive events, that's not always going to be the case. So that one's also false. It's the third one that we finally get one that, okay, there might be a connection there. And that's by saying that we know that they're independent. So this happens, which we're assuming that A and B are not 0. So this is not 0. which means that there's something in the overlap of those two events. that those two events can happen at the same time, and that's what it means to be inclusive. So this is the only one that's really true all the time. The opposite is definitely not true, that independent events, this one is, I would say, never true. So if I was kind of justifying these as like always, sometimes, never, I would say that for sure this one's, whoa, that's weird. This one would be one of those never true concepts. This is an always true. And I would kind of classify both these as sometimes. And maybe not even the first one. Well, I guess I could say the first one, because that would be one of these cases where the probability of A might be 0. And then we have exclusive events that are independent. Okay, so that's to say these, to say true or false and to say always, sometimes, or never true is definitely a different ask. And I was just looking for true or false. Maybe it would have been easier to look at always, sometimes, or never true. So the moral of this story is, I know we want there to be some connection between independence and dependence and exclusive and inclusive, and there's just really not. I mean, other than this one that we can guarantee is true, there's really not that strong of a correlation between the two. Okay, they can be a mix of them, and that's okay. All right. So we're going to look at some probability calculations today. Now, one thing that I do want to talk about, I guess, before we get too far into it, we've dealt with quite a few problems that are related to a deck of cards. And so let's just make sure that everybody's on the same wavelength there. So in a deck of cards, there's 52 cards. In those 52 cards, we have 4 what we call suits. Okay. We have 2 black suits and 2 red suits. We have spades and clubs are the black ones. And then for the red ones, we have hearts and diamonds. And they all come with symbols. A diamond is a diamond shape. A heart is a heart shape. Clubs and spades are ones that people generally aren't too familiar with. That's a pretty bad club, but kind of like that. And spade kind of looks like an upside down heart. Okay. And I mean, that just reminds me when I was a kid, I would always say clovers and shovels, because that's kind of what they look like. Okay. So we've got 4 suits, hearts, diamonds, spades, and clubs. And in that we have 2 colors, the red and the black. In each one of the suits, let's say in each suit, we have 13 what we call ranks. And I think the term ranks in a deck of cards kind of comes from sort of a military background, as in there's a hierarchy. There's definitely ones that are better, ones that are worse, and all that depends on what you're playing, what you're doing with the cards, that kind of thing. But in each suit we have, I guess I'm going to go this way. I didn't plan on it. But 2 through 10. And then we have a jack, a queen, a king, and for some reason I put ace at the front. You can either, a lot of games either put ace at the front or at the, lower than 2 or higher than king, and even some games it can play in both spots. Within those we have these 3 here that are called face cards. King, queen, and jack, because they actually have pictures of people on them. Okay, that's what makes them face cards. They have a face. Some people will say like paint it when they want a face card drawn, just because there's typically face cards are more colorful. Okay, so kind of all that together means that there's 4 2s, there's 4 3s, there's 4 of every one of these ranks in a deck of cards because there's 1 for spades, 1 for clubs, 1 for hearts, 1 for diamonds. Okay. And I think that's pretty good. That would give everybody a decent idea of what's in a deck of cards. So let's go ahead and look at some of those problems, because the first ones, hello, where'd we go? There we are. The first ones deal with that pretty, a lot of them do, because I can only roll a 6-sided die so many times before I get tired of writing problems with a 6-sided die. But definitely when you start looking at a deck of cards, there's so many possibilities and so many categories that it's kind of why cards are used a lot in probability, because of they have things that are similar and a lot of things that are different. So the first one says you randomly choose a card from a standard deck of 52 cards. Find the probability you choose a queen or an ace. And so when we're finding all these, we do need to think about independent, dependent, inclusive, exclusive, because the formulas that we use on those are different. This one happens to be a queen or an ace. That actually happens to be exclusive, because there is no queen that's also an ace. Okay, so when we look at probability of a queen or an ace, now, one thing that I want you to get to seeing pretty quick is that anytime we have or, we want to think about addition. Okay, and that's pretty standard in a lot of areas of math. Since they're exclusive, the probability is just going to be the probability of a queen plus the probability of an ace. There are 4 queens out of 52 cards and 4 aces out of 52 cards. So in total, that's going to give us 8 out of 52, which is going to be, it'll simplify away, as they're both multiples of 4. So that's 2 over 13. If I divide them both by 4. Oftentimes, you're going to be dividing 52 by 4. Realize that it's the 13 ranks of each suit. So there's, 52 divided by 4 is 13. And that can make your life a lot easier. The next one says find the probability that you choose a king or a club. Again, we have or. I'll just say K or club. But since there is a king of clubs, that means that this is inclusive. So we want to take the probability of a king plus the probability of a club minus the probability of pulling the king of clubs. Not a great club symbol, but you get it. Okay. So probability of a king, there's still 4 of them. Probability of a club, that's all the ranks of clubs. So that would be 13 out of 52. And we're going to take away the 1 out of 52 that is the king of clubs. So 4, 13 is 17, minus 1 is 16 out of 52. I don't typically like to reduce these yet, because I know that I'm going to have to add and subtract with them. And that's a little bit easier when I have the 52 as a common denominator. So now they'll both divide by 4. That's going to be 4 over 13. Find the probability you choose a card with an even number or a heart. This one's a little bit tricky, because cards with even numbers, we have 2, 4, 6, 8, and 10. So we have 5 in each suit, in each of the 4 suits. 5 times 4 is 20. So keep that in mind. Probability that we choose an even or a heart. So we said there were 20 evens out of 52. There were 13 hearts. And then we have to ask ourselves, are there even hearts? Well, yeah, there are. There's 2 of hearts, 4 of hearts, 6, 8, and 10 of hearts. So there's 5 that are in the overlap. So we do have to take those 5 away to not double count them. So let's see, that's going to be 33 minus 5 sounds like 28 out of 52. Is that right? Yeah. Again, they're both multiples of 4. A little bit overkill on the multiples of 4, but it makes life a little bit easier. Probability that you choose a heart or a spade. Okay, probability that you choose a heart or a spade. There's 13 hearts. There's 13 spades. There are no spade hearts, so there is no overlap. So we just add those. And we get 26 over 52, which simplifies quite a ways, is 1/2. Which makes sense if there's 4 suits, and I'm saying what is the probability that you pick one suit or another, we're involving half of the deck. So we get a probability of 1/2. Yeah, let's go ahead and do this this problem, and I'm going to change another one somewhere. Sure. I have 2 problems on here that are basically the same thing. So I'll do this one how it is, and I know the other one's coming up. It says a coin is tossed and a 6-sided die is rolled. Find the probability that the coin shows heads. Oops. And the die shows a 5. And the die shows a 5. So these are independent events. Flipping a coin, rolling a die. They're independent. So, yeah, we have probability of heads is 1/2. And if when we see or we think addition, when we see and, we want to think about multiplication. So, and rolling a 5 on the die would be a 1 out of 6 probability. So this turns into 1/12 as an answer. Okay, next one, find the probability that the coin shows tails and the die shows an odd number. So a probability of tails and an odd number. Probability of tails is the same as heads, it's 1/2. Probability of an odd number is 3 out of 6, which is also 1/2. I can reduce that to say that this is 1/2 times 1/2, or I could have multiplied it straight across and I would have got 1 times 3 is 3, 2 times 6 is 12. 3 over 12 would actually reduce to the same thing I get here, 1/4. Okay. The next one I have here is an aquarium contains 6 male and 4 female goldfish. You randomly choose one fish and don't replace it. Then you choose another fish. And we're trying to see what is the probability that they're both male. So we want to say that we're going to pick a male and we're going to pick another male. These events are dependent because I don't put the first goldfish back. So on the first one, there's a 6 out of 10 chance to pick one of the 6 male goldfish out of all 10 that are there. Now, once that one is gone, there's no longer 10 goldfish, and there's no longer 6 male goldfish. There's only 5 male goldfish and 9 total. 6 times 5 is 30. 10 times 9 is 90, and that reduces to 1/3. So this one I want to change. So follow along here. I want to change this to an or, because this would basically be the same as this one here where the coin landed on heads and the die landed on 5. So we're going to change it to or and really take a look at it. So find the probability of rolling a die and landing on 4. So probability that the die lands on 4, or the probability of a coin landing on heads. So you can kind of see if that was and, it would be the same thing. 1 out of 6, 1 out of 2, multiply them together, there we go. The question is, are these inclusive or exclusive? We know they're independent. We said that they were independent. And if we look up at the top, one of the problems we said is that all independent events are inclusive. So inclusive means, well, first of all, we're adding because it's or, but it also means that we have an overlap that we need to subtract out. That one's not overly obvious what it is. So I do know that I can take these and add them together. So the probability of getting a 4 is 1 out of 6. The probability of rolling heads is 1 out of 2. Sorry, flipping heads is 1 out of 2. And then this means that there must be a 4-heart combination, at least one, I guess, when we roll a die and flip a coin. And there is one. There's 1 out of the 12 possible, right? We should know that there's 12 from our counting strategies idea. There's 6 options for this, 2 options for this, multiply those together and we get 12. And there is only one that has a 4 and a heads. So we're going to subtract 1 out of 12. All right, we need common denominators here. Let's make them 12. So this is 2 out of 12 plus 6 out of 12 minus 1 out of 12. 2 plus 6 is 8, minus 1 is 7, so we get 7 out of 12. Okay, find the probability of pulling a blue or green marble out of a bag with 3 green, 4 blue, and 5 red. Well, there's 12 marbles in this bag. So the probability of blue or green, probability of blue is 4 out of 12. Green is 3 out of 12. And there is no overlap because there's no blue-green marble. Oh, look, same answer, 7 out of 12. Interesting. Last one on this side, find the probability of drawing a queen or an even number. So we have queen, or even. Probability of a queen, there's 4 of those out of 52. Even numbers, if we remember, there's 20 out of 52. And even though the queen would fall in line to be an even, it's not an even number, it's a letter. So we don't have to worry about that having an overlap. We get 24 out of 52. There again, both multiples of 4. So we get 6 out of 13. Okay. So let's move on and take a look at a blank screen. Great. Then another one we wrote on. There we go. Now we're going to look at some more computational ones to figure out if they're independent, dependent, inclusive, exclusive. When we don't have scenarios here, it all comes down to the definitions. The definition for something to be independent is that the probability of A and B is equal to the product. P of A times P of B. If that doesn't work, I like to say if not, then they're dependent. If they don't equal, they're dependent. It's about as good as I can do for that. So let's take a look at multiplying some of these and see if we get the result that we want. 1 out of 5 times 9 out of 20. 1 times 9 is 9. 5 times 20 is 100. That does not equal that. So they are dependent. Probably not going to do all these. I just want to do a couple to get a good idea and keep the video length down a little bit. The next one, I have 1/4 times 1/4, which equals 1/16, which is what it said it was. So they are independent. Okay. And I want you to verify for yourself that these are dependent, independent, and dependent. Check the math on those. For inclusive, exclusive, we focus on the inclusive part. We focus on the exclusive part. Exclusive means that the probability of A or B equals the sum of the other two. And again, just like before, if not, then they're inclusive. Okay. So we would have to add some fractions. One downfall to adding fractions is I need common denominators. I'm going to go ahead and write that when I do this one. I'm going to put them both as 20s. 1/5 is actually 4/20 plus 13/20. And when I add those, I do get 17/20. That's the same as what they told me it was. So they are exclusive. The next one, well, we want to relate it to 100s. So I'm going to turn that into a 100. To do that, I need to multiply 20 by 5. So 7 times 5 is 35. Multiply the 5 by 20 to turn it into 100. So 2 times 20 is 40. And this equals 75 over 100. There we go. Which does not equal that. So they are inclusive. And it looks like maybe 14 out of 100 is in the overlap. Maybe. It might be a little. Oh, yeah, that's right. Okay. Go ahead and verify for yourself. Trying to do it in my head, I guess. That these ones are inclusive. And I guess check my answer too. This one is 6 and 5. This one is exclusive. Now the other thing, these two are different because they tell me something about the probability of A and B. The other rule for exclusive is that the overlap is empty, or the A and B equals 0. If it doesn't equal 0, then they're inclusive. So this one here, the overlap is 0. I don't have any work to do other than say that they're exclusive. This one, the overlap is not 0, so they're inclusive. And that's it. So go ahead and double check some of those other ones that I didn't quite finish. Otherwise, let me know if you have any questions. Have a great day, and we'll see you in class.